Okay, let's talk about the final project to start with. So the project is basically an opportunity to kind of apply what you've learned in class. We'll kind of be in the midst of talking about new material as you work on the project. So to try and keep that in mind. And the sort of basic idea is that you learn all these concepts in class, and then you apply some of it in the homework, but really we want the real usefulness of the classes to be able to translate this into like future research efforts. And so I would highly encourage folks to work on problems related to your research, data sets that you might actually use in the future. So in terms of deadlines, so we'll have three major sort of deliverables. There's the project proposal, and then at the end of class, we'll have project presentations and a project report. So the proposal will be due on April 29th, which is, is that next Friday? Something like that. Next Friday. Yeah, so next Friday, the project proposal will be due. And then project presentations are going to be due on the first day of presentations in class, so that everyone kind of has the same amount of time to work. So for the project proposal, some things to think about. What data will you be using for the project? Size of the data set, source. Maybe you can summarize a little bit. What kind of hypotheses do you want to test? There's a little bit more detailed information about this on the rubric, which is in the project folder in the files under Canvas. So make sure to have a look at that. We are doing groups of like 2 or 3, so we can try and make sure we have around 12 to 15 groups so that everyone will have enough time for presentations. And yeah, so for the project proposals, I highly encourage you guys to chat with me or with Vaish about what it is that you'd like to propose. It's just a way for us to make sure that from a sort of scoping perspective, you guys aren't doing too little or too much for the project. And we'll provide more feedback from the proposal as well. For the project presentation, 10 to 15-minute presentation. Again, more sort of details available in the rubric, but basically what you'll be presenting here is things about the data, and even sort of prior to analysis, what sort of interesting findings are there, and then any sort of analytical results that you're getting from there. And then for the project reports, yeah, so don't worry about the length, focus on the contents, talk about the process that you guys took to conduct the analysis, and then employ the sort of techniques that you learned to do your analysis. Yeah, and so again, this is mainly meant hopefully as a bridge to sort of larger analysis in the future. Okay, any questions about the final project? Concerns? All right, it's going to go swimmingly. Yes.
Can you give us a sense of what size of data set?
Yeah, so it really varies. I've had people use fairly small data sets like a couple columns, couple hundred data points type of thing. And I've had people use absolutely ginormous data sets before, talking about like hundreds of columns, even millions of rows. So really it encompasses a lot. the way that you end up scoping your analysis can help sort of deal with size issues in the data if it gets really big. So just because you have a really big data set doesn't mean you can't use that for this analysis. Yeah, so as long as there aren't too many individual ones, then yeah. We might have to, yeah, okay, so depending on the number of groups, like we might have to spread out presentations over more days. So if it comes to that, we might have like a set of presentations on finals week. So yeah, you can do individual, but I would encourage, yeah, doing it in groups. Yes. Sure. Let's look at last year's last year's projects. Okay. Spring final projects reports. Okay. Wow, long title. Investigation of different demographical characteristics in business establishments that could potentially have an impact. Oh, okay, yes. I don't know why this title was so long. So this one, they were looking at essentially how attributes of like of cities and neighborhoods could affect traffic in certain areas. Let's look at a different one. Whoa. Will your next car be electric? Okay, clustering of EV public charging data, understanding charging behavior. So this analysis was using charging provider data to get at clustering locations and understanding where deployments happen. Let's see what else. These preview things are really bad. Okay, here we go. Electricity price forecasting. So this one was using neural networks, machine learning, which you learn about sort of way at the end of class, although he already has had some expertise in this area. Yeah, and so looking at forecasting electricity prices. Let's see what else. Oh, how electric vehicle rebates affect electric vehicle adoptions in California. Predicting preferences for alternative fuel vehicles. So similar type of thing here. Oh. Am I still here? Yeah. Okay, does that give you some maybe sense of things? A lot of what I'll say about this is that a lot of the projects here are pretty closely related to some of the research efforts that that those students were doing already. Yeah, you can. Yeah. Yeah, to supplement your analysis, that's perfectly fine. Okay, any other questions? Okay, so let's go back to our lecture. All right, so let's start off today. We're going to be talking about a different type of variable. So everything we've talked about so far has been regarding sort of continuous data. In other words, the values that any of your variables take on can essentially range from negative infinity up to positive infinity. We'll talk about some of the sort of deeper implications of that later, but there are other common types of variables that you guys might experience in your data sets. So these are dummy and categorical variables. Okay, so the dummy variable is a variable with only ones or zeros to indicate the outcome. Okay, so basically, this is a type of binary variable, can only take two values. You could denote them as the actual things that you're looking at, or you can denote them as sort of ones and zeros as a representation of those. So like what might be an example of a binary variable? So if you are looking at gender, for example, you have male and female, that's sort of two options. So you could have one as either your male or female and zero as the other one. And that would be a way to indicate, right, a particular type of outcome. Flipping a coin, heads or tails, another type of a sort of dummy variable. So a categorical variable is essentially a generalized version of this. So this is a variable that can take a number of fixed values, fixed possible values. So the idea is that similar to the dummy variable, it's doing a discrete set of values, but you can have more than two. Okay, so a dummy variable is actually a type of categorical variable. It's a subset of this where you can only have two possible values, but for a categorical variable, you can have sort of as many discrete values as you want, right? And so common examples of this would be things like in demographics, right? Like education level, political affiliation, okay. Any confusion here? So let's take a look at these types of variables in sort of a practical example. I think this is the easiest way to sort of get a grasp of how these work and how you can integrate them into regressions. So we'll just go ahead and jump over to R. I guess I didn't need to raise it the first time, huh? Okay, great. Let's start a new worksheet over here. And okay, let me navigate over to my lecture 7. Let's set this as the working directory. Okay. And I'm going to load in a data set called wages. And let's go ahead and let's take a look at this data. Okay, it's pretty straightforward. There are 6 columns here. Earnings here, which is the annual wages, each row corresponding to an individual. And then we have a couple different attributes about that person: their height, their gender, their race. ED stands for education, and the number here corresponds to the number of years of education that they have. And then lastly, we have a variable called age. Okay. So as I was mentioning before, when we have been looking at the sort of past examples of regression, we've mainly been dealing in the sort of continuous domain. But you see these 2 variables of sex and race are both variables, categorical variables with discrete values. So they have these text, right, instead of numbers. And we can still sort of run a regression on this. Okay, so we are going to do just that. And actually, if I look at the structure of wages really quickly, we'll notice that we have a couple numeric ones, a couple characters, and then a couple sort of integer variables. So I'm going to create a model here. And let's take a look at what this is going to tell us. So this is going to be a multivariable model. And you'll notice one extra thing that I'm doing here, which is that the gender variable I'm including as a factor. So if you recall, the factor is this weird thing, right, that makes categorical variables into this specific data type that has these levels. And that's simply a way for this regression model to kind of understand that what I'm feeding it is some kind of categorical variable. Otherwise, it's like you're trying to do math on words, right? Which doesn't really kind of make sense. So I can run this. And let's take a look at the results. Summary wage.model. Okay, so these are going to be the main set of results that we care about. So we have three variables: education, age, and gender, as well as your sort of intercept here. So let's talk about kind of what this means. And I'm going to ask you guys to help me out here. So who can help me sort of walk through these coefficient estimates, kind of based on what we've learned so far? Anyone? Yeah. So okay, let's walk through this one at a time. So let's start with education. So what is this kind of telling you?
The higher the education value,
Yep.
the more money.
Okay, and so if I, on average, in the data, we observe that one additional year of education gets you how much more money? Yes, $4,469. If you are older, so okay, let's look at this guy. What is this telling us? Yeah, so for every year of age that you are, you make $280 more. Okay, great. So these are like the two kind of more straightforward ones. Here, this is kind of interesting. We have this extra thing here that's telling us male. So how many categories of variables, or sorry, how many outcomes of the categorical variable are there? 2. Okay, but it's only showing us 1. So does anyone have an idea of what's going on here? Yeah.
It's holding female as default.
Yeah. Yeah, exactly. So let's maybe draw this on the board. Okay, so let's do, so the intercept here, let's say hypothetically that you are 0 years old and that you have no education. Okay. This is kind of out of bounds of this regression, but let's just assume that for now. So we can ignore these guys. And so if you were a female, your expected income would be how much? Yeah, that would be for the male one. But for the female, the way this works is that in these regressions, you have these zeros and ones. And one of those values in a categorical variable will always be omitted and set as the default. The way that R does this is it sets it as just alphabetical order. So F becomes before M, so female is the default value. So for females, 0, 0, actually the starting salary would be negative 47,907. So here, so this is negative 47,000. Let me actually put that on the negative 47,907. Okay, and so this is female intercept. And then for categorical variables, it modifies the intercept. So this is going to be plus 21,000. So for the male, it would be something like this, minus 36,000-ish. Yeah. Okay, so if I look at the equation, so wages is equal to beta 0, which will be my intercept, plus beta 1 times age, plus beta 2 times, oh, sorry, beta 1 times education. Beta 2 times age, plus beta 3 of sex. Okay, so let's see what's happening here. So this value can just be a 0 or a 1, okay? So if it's 0, this is female. And if it's 1, it's male. So when you're 0 here, this will be beta 3 times 0. Okay, so this value becomes 0. So the female is the intercept plus your education effect plus your age effect. The male one is beta 3 times 1. So beta 3 is this 21,000. So it'd be 21,000 plus your intercept, and then plus the effect of education and age. Yes. 26. Yes. Sorry. I'm bad at math. You add 47,000 to 21,000. Yep. And if I were to look at the effect of, for example, age on here, you would have two lines, one like this for males, and one like this for females. And we'll notice that the slope of this line, beta 2, okay, so this is slope equals beta 2. The slope of these two lines will be the same between males and females, right? If I have 0, or if this is 1, beta 2 doesn't change. Okay. But you will have sort of separate lines for each of these. This would be assuming that your education is being held constant in this case. Questions about this? Yes, it is a dummy variable because there's only two outcomes. Okay. Any other questions? In this case, yeah. But there's a different sort of plot, right? This could be hope I'm not confusing people, but you could have a different slope here if this were beta 1. Oops, education. There's another set of slopes for education as well. And those lines would be slightly different, but both of them would intersect here at your intercept points along your y-axis. Does that make sense? Yeah, yeah. So, okay, so you'll have one plot like this, okay, where this rise over run would be 4469, 4469, and then you're going to have a different plot, right, where maybe the lines look like this. These would be negative 47K, negative 27K, and then this would be males, females for age, and this would be a slope of beta 2. So you'll have both of these sort of plots. If you imagine this in like 3 dimensions, you could have a plane that would represent the sort of line across dimensions of both education and age, but that gets really hard to draw. So we just look at them independently. Okay. Let me jump back over to the code. Okay. So how good is this model? we look at the R squared a little bit, but one of the ones that I had encouraged everyone to look at is the residuals. So I'm going on a bit of a sort of tangent here, but always important to do this in practice. And what you'll notice, okay. So here's a plot of the residuals. Opinions? Does this look thumbs up for good or thumbs down for bad? What do you guys think? I see a thumbs down. Thumbs down. Okay, so why are you, what's your sort of initial gut reaction? There's this like weird line here, right? So what do we look for in our residuals again? Someone remind me. 0, yeah, and sort of randomly distributed, right? So there's this line here that definitely doesn't look very random. So what the heck is going on? So one of the things that we might find is that in a lot of these regressions, right, like you can ask ourselves, like, what might be causing this type of thing to happen? And one of the things is that you don't see values sort of below a certain point. So if there's some kind of like cutoff in your data, that can be one of the reasons why this happens. And so can anyone think of a cutoff that might be appearing in this data as it pertains to wages? No one? Yeah, there's no wages below like 0, right? And so that might be one of the reasons. So one of the common ways that people deal with this is when you have, so in your data, so the sort of distribution of values that you observe, one of the ways that you can make them sort of all distributed in such a way as to avoid that is to do a log transformation. So we'll do that and we'll take a look at what that will do. And I'm just going to go ahead and, so this is more kind of a walkthrough of how I might try and deal with these residuals. So in some cases you have some NAs. Okay. And in this case, it looks like we now have sort of a better clustering sort of points here, but then there's still this very clear set of points that look like this. So it turns out, if you kind of dive into this and look a little bit closer, there are a set of sort of outlier points where you have extremely low wages. And so this might be related to, someone who might be like a student or something. Actually, in some cases, these might even be sort of zero, or there might even be some negative ones. So one thing we can do if we want to just focus on the rest of the cluster is to filter out those data points, which is what I'll do here. Where in the data, I will look at only wages where the earnings are more than 1,500. And in this case, once I plot this, okay, now we can see that our residuals are kind of sort of much more in line with the set of residuals that we would hope to see in a residual plot. Okay. And so this is, okay, thank you, Siri. So this was kind of a little sidetrack here, but this is hopefully providing a little bit of insight in the steps that one might take as you identify problematic residuals, how you might sort of go about trying to fix that. And so these are literally kind of the steps that I took when I went through the data and started running these models. Check the residuals, see there's a problem. Okay, like see if I can identify this. How can I sort of either manipulate the model or to sort of identify problems in the data itself until I sort of arrive at this thing, right? And so we should always sort of keep in context like what this new model does, what it describes, and how it should be interpreted, sort of falling on whatever it is that we sort of have done to manipulate the data or the model. And so if I were to look at this set of results and I say, okay, summary wage.model.log. Okay, we have this new set of interpretations, right? Especially because like y is now logged. So then you have this whole thing about like, okay, as education goes up by 1, that changes y by some percentage, right? That's the interpretations that we were going through last time. But also when I kind of describe these results, I've now sort of filtered out wages below 1,500, right? And so I should be careful about the way I describe this in saying that, okay, so for people who make more than $1,500 a year, we observe these sort of relationships, okay? And so as you interpret the model, you wanna sort of caveat everything and couch it in sort of a proper interpretation based on all the things that you've done, right? This is no longer sort of universally applying to this data set. It's only applying to everyone making more than this $1,500 a year. Okay. Any questions about that?
How did you arrive at the 1,500? Like, not just the number, like, if the problem is with the wages below certain level.
Yeah. So if we go back to this guy here, and actually, let's do this one. basically what I did is that I pulled out all of these data points into like a separate table. And you can do that by sort of estimating a line here and then grabbing all the points below that line. And then I observed in the table what was consistently happening with that data. And they all had sort of relatively small wages, annual wages, below some cutoff. And so if I compare that against all of these other points, I found that these guys were basically all the ones that were sort of below 1,000. So I just made this arbitrary cutoff to get rid of these points. Does that make sense?
Not totally, but
It's a little bit arbitrary. It's so that I didn't have to like have a bunch of code to confuse everyone on grabbing all of these exact points. Because it is a little bit confusing the way that I grabbed all of these. Okay, yes.
If you wanted to explain what's happening there with the people that earn less than 1,500, you have to do like another regression with other factors.
Yeah, you could. You certainly could do that. But I guess what I would say about those data points is that the way I would almost characterize this data set is that it includes people who are like regular working with sort of regular jobs, I would say. I mean, not even regular jobs, but the data set also includes people who are clearly like sort of temporary workers or people who aren't sort of consistently, I guess, bringing in income. It looks like it's like side income basically, because there's a really big gap between the sort of size of the wages. Even if you're sort of a low income earner, you know, you're still earning on the order of tens of thousands of dollars a year compared to, you know, if you're like babysitting once or twice. And so the sort of variability of all of these points and what you're going to kind of derive from them is going to be sort of systematically different from the rest of the data points. So I think even running a regression on those guys separately, I haven't tried it, but I don't think that it's going to tell you that much. It'll be pretty random, I think.
and like when I look at the line,
Yeah.
where it ends, is that the point like you kind of approximated as like, okay, below this line, like on the x-axis, if I look at it, the wage model log, that's like ending about 9 or like 10. Does it give you an idea, the x-axis?
So the x-axis here, this thing here,
Yeah.
for the limit, not necessarily. I mean, it's kind of hard to derive because this isn't just the sort of way, it's the wage versus the error, right? So it's not necessarily having to do just with what you're reading off of here. When you're looking at this type of thing, the best thing that you can do in this case, when you observe this like problematic residual plot, is to like go into the data and see what it is about these particular points that's leading to a specific type of, because it could be it could also, this trend could also be related to your explanatory variables as well, right? And so you have to see what it is sort of across the sort of different dimensions of the data that bring you to a particular conclusion to want to filter it. Yeah. Yeah. So the way that I did it was I don't know if there's always like an easy way of doing this, but essentially I said, okay, if I had a line that went like this, grab all the points below that line. So there was kind of a little bit of work behind the scenes to do that here. Okay. That was a bit of a tangent, but again, hopefully useful. Let me actually make a new data set called wages clean, which will just be wages earned greater than 1,500. And we'll run our new models on this. So wage.model. Okay, so one of the things that we haven't looked at is doing our regression against a full categorical variable that has more than sort of 2 levels. So let's see what happens if I do this. Okay. So here, we have a new set of results. And let's see if we can interpret what this means. Okay, so now I have a new model for wages where I'm regressing wages only on our race categorical variable. So it will look something like this. Wages is equal to beta 0, our intercept, plus beta 1 times race. So effectively, what this is going to look like will be this. If I have sort of 4 levels, you'll have beta 1 times Hispanic, or I'm going to use a different variable here just to make it not confusing, or hopefully less confusing, plus alpha 2 times other plus this times white. Okay. So these are kind of equivalent. This line here is essentially what's happening sort of behind the scenes. Okay, when you have race, you can take on so effectively 3 different values, even though there's 4 levels. Okay, so in this line, these are all sort of tied to each other, right? If you are one of these things, you cannot be any of these other things. So if Hispanic is white, then these other ones have to be 0. So that's one configuration. Another configuration would be 0, 1, 0, right? Another configuration would be 0, 0, 1. And there's actually one more configuration, which would be 0, 0, 0. Okay. So let's take a look at what this would look like graphically. So this is wages. And this is actually, there's not really anything on this axis, but we'll just kind of draw this for now. Okay. So the first thing to note, actually, I will get rid of this. Okay, so what is our base value here? Yes. Okay, and so that is going to be 31,813. So I will have some value here. So this is at $31,813. And this is if you are Black. And the configuration here is if you're Black, that's 0, 0, 0. And then your intercept would represent the sort of base value of that race. Okay. If you are Hispanic, then on average, we observe from the data that you make $2,230 less than if you're Black. So this would be 1, and these two would be 0. And so that would be a little bit below this. So this would be 29,600. So 29.6 thousand. Okay. We have another configuration. So if you are, if you are other, you make 5,510 more than if you are Black. So that would be 55, so 36, 37.2. So this is other. And then lastly, if you are white, 6,800 more. So that would be actually 1,300 above this. So this would be something like 38.5K. Okay. So here we can see that there are 4 levels that you essentially are able to derive out of this model, even though it only looks like there's 3, right? Again, it's the same thing. You leave one out as the default, which is represented by the intercept. If you have multiple categorical or dummy variables, it's the same rule, right? So let's say we have wages is equal to beta 0 plus beta 1 race plus beta 2 it's sex. So in both of my categorical variables, dummy variable in this case, you would omit one of the levels. Okay, and so if we remember in sex, we omit female, and then in race, we omit black. So our base intercept value would be for female, black. And then all the sort of modifiers of the values that you see in the model will modify your intercept in some way. Okay, does anyone have any questions so far about this? Yeah. Yeah, it does. Yeah, it'll pick it by alphabetical order. And if you want it to omit a specific one, we can actually do that. So the way you would do that is like this. So in the factor, you could change the reference to white. And in fact, what we should find, oh, I need to change this to that factor first. Oops. Okay. So I'm just going to copy and paste the model again. What am I doing? Am I going too fast? Wait a minute. Uh-oh. Oh, my bad. This has to be wages.clean. We'll get there. Okay. So you'll see that when I re-level, it changes the reference. So now my intercept is white instead of black. Yeah. Okay, so let me actually scroll back up to this guy here. Okay, so this part is a little bit tricky, but if you think about the way that we've been interpreting this, hopefully you'll get a good sort of grasp of what's going on here. So, okay, so forget about everything else here. Let's just look at the intercept. So for people who are black, there's this estimate that your average annual income is about $32,000 a year with a standard error of about $3,000. And so the standard error, right, is testing a specific hypothesis that this value is greater than or different from 0, okay? And we can say with pretty high confidence that this wage is a sort of is statistically different from 0, and therefore, if you are Black, you are making more than $0 a year. Okay, and in fact, in this case, we are almost 11 standard error values away from that 0 value. So we can be very confident, right, that this is a non-zero value. Okay, let's look at the interpretation for each of these. So this says if you are Hispanic, you are making $2,000 less than people who are Black on average. Okay, but the standard error is about $4,800, and we are no longer statistically significant. So what does that mean in the context of this particular problem? This is saying the difference between the Hispanic and if you are Black, that income difference is not statistically significant, which means that in our model, we're not necessarily confident that if you're Hispanic, you're making a different income from if you're Black. It doesn't mean, right, that we think if you're Hispanic, that you are making an income of 0, right? Because this has to get modified by the intercept. So all of these estimates and the sort of standard errors associated with the estimates are sort of relative to your base level value. So instead of saying, is this, are Hispanic wages statistically significant as a way to represent whether or not they're making $0 or not, that is not the right interpretation. It is whether or not you are different from this initial value. So for both other and for Hispanic, because these are not statistically significant, that is an indication that we don't think it's super likely that the differences in the wages between Blacks, Hispanics, and other are something that we're actually observing in the data, that they are different. If you are white, there is a statistical difference. So 6,800 has a p-value of about 2.5%, which indicates that on average, people who are white have a higher wage than people who are Black, like 97.5% of the time. Okay. Any questions about that? All right. The last set of things that I'll talk about related to this is a third type of variable known as an interaction variable. Let me make sure I'm okay. Okay, so this is relationship among 3 or more variables if the influence on the third is not additive. Okay, what the heck does that mean? Consider something like this. Beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. Okay, let's look at this in the context of our sort of wages example. So we have something like this. Wage. So you have, I guess it was, okay, so we ran our regression with wages looking at differences between males and females. You can run your regression separately on, let's say, education, and you'll find some kind of line that looks like this, right? So as your education increases, the more money that you make. We can combine these two and I would have something that looks like this. So where you have male and female. So you'll have 2 parallel lines that capture the effect of wages as well as gender. But what if you hypothesize that the slope of these 2 lines could be different? Okay, and so that's where this comes in. I can do something like this. Because when I don't have this term here, the effect of, let's say this is education and this is gender, these are independent, which means no matter what gender you are, the slope on education will always be the same, okay? But we can modify that by including these interaction variables, which is an important technique if you suspect that there is a difference, right? If there's some kind of interaction term that allows for these to not be independent. So let's look at that here. Okay. So wage model 1, earn sex data equals wages dot clean. Okay, so let's take a quick look at this. So in this case, here, females make on average 30K, males make on average 17K more. Okay, so that's kind of this plot right here. We can do wage model 2. Okay, and in this case, we start out with an intercept of negative 21,000, and for every additional year of education that you receive, you make $4,300 more. Okay, so that looks like this. Let's take a look at the next one. Okay, so we're starting to get a little bit more complicated. The education parameter 4250. So the slope of both of these lines here is the same, 4250. But if you are female, your intercept here is going to be lower than if you are male. This is at negative 29,000, and this would be negative 27,000, and this would be negative 27,000 plus 16,000. So this would be something like negative 10-ish thousand here. Okay. And let's look at the last one. So the way that you can do an interaction variable is pretty straightforward. You just multiply these guys together, write in the equation, in the regression equation like so. And let's take a look at this. Okay, so we now have this extra interaction term. Okay, so what does that look like? So you'll notice that the interaction term, one of these is continuous, one of these is a categorical dummy variable. So this is referring to the categorical value that this applies to. So if you are male on the sort of categorical side of this interaction term, if you are female, x2 would be 0, okay? And so then this whole thing would be 0, and these values, sorry, there should probably also be an intercept plus beta 0. So let's take a look at this. So we know that our intercept is in reference to the base value of being female. Okay. And that's going to be this value right here. The male intercept is simply this value plus this value, which actually is going to be lower in this case. So actually, let me modify this line just to be a little bit more accurate. Okay, so actually it ends up looking something like this. So you'll notice in this case that now on the intercept value, males end up being lower compared to before where they were higher. But we'll notice that now in kind of an analogous way, we now have sort of, instead of just different intercepts, you also have different slopes, okay? And so this education slope is the base level referring to the education slope for the female. So that's 3,500 per year of education. But for males, you modify the slope so that it's 3,500 plus 1,500. So that's like 5,000 per year of education for males here. And so this will have a steeper slope and it'll look something like this based on the values that we're seeing coming out of the model. Okay. This can be, I guess, a little bit confusing to digest, especially if you're not sort of familiar with this. So yeah, if there's anything confusing about this, you know, please let me know. I'm happy to elucidate more, but you're also able to kind of review this on your own as well, because I'll include all the code on Canvas. Okay, any immediate confusion here? All right. So now, oh yeah, sorry. Yes, go ahead. Yes, yeah. We will be talking about model selection next class. Model selection refers to this idea that, okay, let me jump on back to my data. Let's do view wages. This is a pretty small data set in the sense that there's not that many different variables, right? You could imagine a sort of much larger or much wider data set with many variables, and there's rapidly becomes this question of like, okay, I have all this data, like how do I formulate which variables I want to include in the model? And we're going to show kind of techniques that you can do to help sort of filter through some of these. The interaction terms is an interesting one and a tricky one. You can interact variables together, and you can interact multiple variables together too. You could actually do sort of x1, x2, and x3. And that can often be a good technique if you suspect that there are sort of relationships between variables that should influence some of the model outcomes. But if you are doing it sort of just kind of randomly and you just want to look at different combinations, that can be problematic because you can run into a huge number of variables very quickly. That can make a lot of the selection techniques that we're going to look at difficult to apply. So let's look at even this simple example here. Okay, we have our response variable of earnings, and then we have 5 potential different explanatory variables. So how many how many combinations of variables could we have? Okay, let me back up and simplify this. So if we have, so number of variables, and then combinations for model. So number of combinations for model. So if we have just two variables, so pretend, for example, this only had like height and sex, for example. You can have x1, x2, x1 plus x2, and then you can have the interaction term x1 plus x2 plus x1, x2. So if we were just looking at non-interactions, you have 3 combinations. If you're looking with the interaction terms, you have 4 combinations, right? 3 variables. You have x1, x2, x3, x1 plus x2, x1 plus x3, x1 or x2 plus x3, and then x1 plus x2 plus x3. So we have, what is this? 5, 6, 7 different combinations of things that you could select for. But then if you include interactions, you can have x1, let's see, x1, x2, x1, x3, x2, x3, and then x1, x2, x3. Oh, sorry, x1, x2, x3. So these 4 can be applied to each of these. So you'd have 28 possibilities. So the number of combinations of possible variables or possible model specifications, as you increase the number of variables, already increases in a sort of nonlinear fashion. But if you include all of the possible interaction terms, it increases even faster, right? Once you're even at like 6 or 7 variables, including all the interaction possibilities is already like computationally almost infeasible for a lot of sort of practical methods. So interaction terms, we typically reserve for things where we have sort of predetermined hypotheses about terms that may influence each other. And you can do like a more limited sort of search of interaction terms as well, if you have some kind of suspicion that there is some interaction. But doing sort of all the combinations is very sort of difficult to do. You're rapidly straying into some things that have to do with like overfitting as well, because it's the number of parameters that you have versus the number of observations will sort of rapidly catch up. Well, we'll talk about this concept later. Yeah, and so you can do interactions, but again, kind of general rule of thumb is to reserve those for things where you already have a suspicion that that's happening. Okay. Let's talk about we're going to talk about a slightly sort of different topic now. And this is going to relate to a lot of future techniques, including already some of the model selection stuff that we'll be talking about next class. And this is about an additional sort of diagnostic tool to measure the goodness of a model. Okay. So this concept is known as out of sample validation. So we've talked about a whole bunch of different sort of metrics, R-squared, standard errors, looking at residuals, looking at mean squared errors, all as sort of diagnostic tools for how good a model is. This is kind of in the same vein, but takes this approach in a very sort of different way. And the idea is, well, you have these models that talk about these relationships between variables, right? So that's the whole point of the regressions. It's like we have x's that are changing, and we kind of want to figure out how that relates to y's. Ultimately, like, isn't the point of the model to kind of be able to accurately tell us about these relationships? And what better way to test the ability of the model to tell us that than to run the model on data that it didn't train on and see how well it does? That's what out of sample validation is. So the basic concept is something like this. You have some what we call training data. And this goes to calibrate a model. Okay. So this is like y equals beta x. This is figuring out what my betas are. That's what I mean by sort of calibrating the model. Okay. So then we take the model and maybe you add what's known as testing data. Oh, hang on. Maybe I'll do it like this. Calibrate model. So this is my the test model. We'll do it like this. And I can have testing data which I can apply to this model. And then we can look at things like R-squared, standard error, residuals, the MSE. Okay, and then maybe we can sort of recalibrate the model. So this basically, this schematic, right, is where you have some alternative set of data that wasn't used to calibrate the model that we can use to evaluate certain metrics. And then in some cases later, we'll talk about how you can sort of recalibrate the model. But the basic idea is that the training data and the testing data should be sort of separate. Sometimes you'll see people, well, they'll calibrate the model and then they'll test it and they'll run it against some data and they'll say, oh, we got these really, really accurate predictions, or the model seems to be really good, but then they're actually not, they're just feeding back data that they already calibrated on, which is sort of less than useful. And so this basically tells us how our model holds up when you do certain types of prediction. So this is kind of an interesting concept, but it's difficult because this idea of having sort of training data and testing data, usually you want sort of as much data as possible to calibrate your model, okay? The more data, typically, the more accurate your beta values are. And so it's not very often that, it's not, okay, I'll caveat that a little bit, but it's not super often that you're gonna have like a separate set of training data and a separate set of testing data. Sometimes you will. There are like these, hackathon competitions where they like give you training data and then later you sort of test it on something. But generally, right, you get some kind of data set and then you would like to run your model on that whole sort of data set. So there is a special sort of technique that can help you kind of employ this framework with a single data set. And that is known as cross-validation. So this is a technique where we use our data to artificially generate a test set. So this looks something like this. We have our full data set. And then what we end up doing is we separate it into two chunks. So this piece would be like this. And you do this sort of separation multiple times. So the basic idea might be something like this, where, oops, I need to stop my screen share here. So the basic idea might be something like, if I have X and Y, and I have a bunch of data in here, let's say A, B, C, D, E, F, G, H, I, J. Let's say I randomly divide this data. So what I'll do is, through some kind of random selection procedure, I'm going to assign into certain groups, maybe like this. Okay, and so the idea here is that I've kind of randomly assigned my data, and I will run a regression against this data, but I'm going to leave one of these groups out. So let's take all the reds out, set them aside. These guys are going to be my testing data, and I'm going to run the model on all the rest of it. And then I'm going to do that again. Let's now take out the green green assignments, run the model, and then do it again where I leave out the blue ones. So this technique is called k-fold cross-validation. Okay, and so this is the technique that we can use to that's the name of the technique where we're sort of leveraging our actual data and randomly creating sort of test sets out of it. Okay, so we're out of time for today. I'm gonna jump back onto this the beginning of next class, and we'll go through developing kind of an algorithm to do this sort of exact technique. Homework 2 has been assigned, so you guys should have access to it now. It'll be due next week on Thursday. And yep, I will see you guys all in 2 days.